Great, thank you. Okay. Okay, hey there, everyone. Thank you so much for joining us today. We really appreciate it. We have quite a group on here, but let me just start by hoping that everyone's doing well, you're staying safe, and hopefully you're getting your vaccinations. If not yet, sometime soon. Today, we actually are going to do an Usher 2020 update, but it's Usher 2020 in name only. We are a community. Hold on a second. I can't get this to, there we go. We are a community, and we are a community of people with Usher syndrome, families of people with Usher syndrome, researchers, donors, people who just care a lot about us. And we are from all over the world. So on this call today, we have people from all over the United States, Louisiana, New York, Florida, California, Texas. But we also have people from all over the world. We have people from Germany, Denmark, Israel. Hold on, Scott just asked me to record, and I did think I was recording. Okay, sorry. So we have people from all over the world that are joining us as well. So we're actually a small community because we're a rare disease, but we, as my daughter would say, we're small but mighty. So we've made a lot of difference in this fight, this struggle that we all have together. So I'm just going to briefly go over some things to catch everybody up on Usher 2020. When we started this about 8 years ago, our mission was to slow, stop, or reverse the degeneration of sight caused by Usher syndrome. At that time, our naive goal was to have treatments to patients by the year 2020. We figured we had some money, we're going to make it happen. Really, we've always had the goal of putting ourselves, and we continue to have the goal of putting ourselves out of business per se. We don't want to be doing this. We want the treatments to be to patients, to our family members, and we want to move on. We all want to move on with our lives. 2020 certainly was a challenging year in and of itself, but reaching that goal was difficult. And the reason is that science moves really slowly. You can't make things grow any faster in a dish. You can't, if you want to create an animal model, it takes a lot of time. Really, it's just not a fast process no matter what. Now, people would differ when you see what just happened with the COVID vaccines, but that took a lot of money and a lot of collaboration that doesn't normally occur in science. And also, it took some really being confident in the scientists and what they were doing to move it forward without a longer term studies. So science does move slowly, but what we also found out that there really is no collaboration going on between researchers in science. They're all working in their own silos. Academia makes it so that researchers don't necessarily want to work together because they're all going for grants and they don't want anything to be stolen. So there's just not the collaboration that's needed to move science forward. On top of that, academics don't know how to bring treatments to patients. They work on little pieces of science, or even if they're working on the bigger picture, they don't really understand drug development. They don't understand how to take something from the lab and get it to a clinical trial and put it in patients. And the biggest thing for us is rare diseases pose additional challenges. Obviously, not a lot of patients, not a lot of money going into research, not a lot of people working on it. So all of those things we faced in our first 8 years. So really briefly, I just want to go through what we did over these past years. When we started in 2013, we just went out and started reading papers and talking to scientists, going to meetings like FFB was having, just trying to learn as much as we could. So in our first full year, we really spent our time doing that research. We did find our first funding group, which was through Massachusetts Eye and Ear Institute, MEI, that's out of Boston and associated with Harvard. And we started funding them through the Foundation Fighting Blindness for a gene therapy vector development and an USH1C corrected gene. And we're really glad we did that, because if you fast forward to right now, when we talk a little bit about gene therapy, that work that was done at that time is critical to what we're doing right now. But the other really important thing we did in our first full year was we put together a consortium of researchers from around the world that were already working on Usher syndrome, and some of them specifically USH1C. And we got people from, again, all around the world. We brought them together and we just said, what do we need to do to start collaboration, and how do we need to find what's going on out there, and how do we make everybody work together to bring treatments to patients. And we came away from that consortium realizing that we needed to promote collaboration, we needed to have a natural history study, and we needed to have a large animal model, because at the time there was only a mouse model out of LSU. And that's not good enough to get treatments into clinical trials in most cases. So from 2014 to 16, we honed our search and we really started heavily funding our researchers. We were funding LSU, Jennifer Lentz out of Louisiana on her antisense oligonucleotide. We were funding the University of Iowa, Ed Stone and Bud Tucker to develop induced pluripotent stem cell program, and also an USH1C gene therapy, or what we were hoping was going to come about from that.
Hey, Susie, can you just check, make sure the captions are back on? They've stopped. It should be on the bottom. Maybe when you were going to do the record, you hit that.
And it's not coming up on the bottom. So maybe you can come in and make sure. Sorry about that on the captions, guys. We were trying to make this work. It's the first time we've used them, however.
Well, that's not right. We have people who are deaf and they need captions, as you know.
Yeah, yep, you're right, Jill. We're trying to get it, I know.
Okay.
Sorry about that. It was,
How'd we get over on that?
I hadn't changed anything. I know.
All right, hang on a
We
second.
can't sign everybody on
Okay.
that.
It's just gonna take 1 second. We're gonna.
Sorry, guys. Can I keep going? I do apologize.
Of course, we
You're
know.
working, duly spelled wrong. When you're working with something new, it's always a problem.
Isn't that the truth?
All right, I apologize to everybody. We're not really sure what happened, but somehow with the closed captioning, it got flipped back over to the wrong account. And without knocking everybody off and starting over, and not even sure that's going to work, we are not going to be able to get the closed caption on. But what we will do, and I really apologize for this, is we will make sure that a transcript comes of this presentation, and we are recording it. So we will put out a transcript, and I hope that will be enough. I do have slides that have pretty much everything I'm saying written down, just not in the detail. So you should be able to follow along with that as well. I do apologize. So let me keep going forward at this point though. So finally in 2014 to 16, the other researcher we started funding was the University of Mainz. This is Uwe Wolfram and Kirsten Nagel Wolfram to develop both a large animal model and to do some isoform study, which I'll explain what that is a little bit later. Really our pivotal year came in 2017. And the reason that this was pivotal is because of the research of Jen Lentz at LSU, the antisense oligonucleotide was actually ready to go to the clinic. Now, this particular treatment would only work on the 216G to A mutation of USH1C. So the population of that particular program was going to be really, really small, even smaller than the USH1C gene alone. So what happened is when we went to take it when we tried to take it to clinic, we found out that the company that made the oligonucleotide would not allow us to take it. They wouldn't fund it. They wouldn't allow us to take it and fund it. So basically they were letting the researcher use it to do their research, but because of probably mostly the small patient size, they didn't plan on ever taking it to the clinic. So Scott went all around the country, the world, talked to everybody to see if we could find another path. And we pretty much found out because of the small patient size, it just wasn't going to happen. So that made us realize that no matter what we do, are we really going to be able to get this into patients? And that's where Odelia Therapeutics came from. So we created Odelia with Luke Vandenberg and Eric Pierce, and it was really Scott, when I say we, Scott, out of Luke and Eric out of MEI, created it to figure a way to bring rare gene therapies from the lab into clinical trials so that they can go to patients. So that's what Odelia was all about. It is a nonprofit biotech. So it's just like Usher 2020, but it has a more broad goal in mind, not just for Usher syndrome, not just for USH1C, but for all rare diseases. And they're working along. It's again a long, hard slog, but they're doing a lot of great things. And you're going to hear more about Odelia as we talk about the gene therapy program that we're funding. And we also, during this pivotal year of 2017, cloned our first USH1C model, large animal model, which we needed to move forward. So through 2018 and 19, we actually specialized and diversified. So we tried to say, okay, what do we have that we're working on that's actually going to go anywhere? So we specialized. So we took our treatments, 2 treatments that we're going to talk about next were the ones we're specializing in, but we also diversified by working with NIH and NEI, thanks to funding from the Mendel family. We worked with them to develop an organoid for testing of drug treatments. And we also diversified by going to Johns Hopkins and funding the extension study for NAC, which I'll talk about in just a few minutes. Finally, in 2020, although it was a crazy year for everybody, we did do some really great things in that Odelia Therapeutics took over our gene therapy program and put together a 2-year plan to test our gene therapy so that we can move into clinical trials after that 2-year time frame. A very aggressive 2-year time frame, but we're hoping for it. And then we also did some ancillary support for the NAC program because they are going to start a 4-year clinical trial, hopefully by the end of this year. So the important thing to remember right now is what we're looking at is urgency. We need to get our treatments out of the lab and into patients because Clinical trials take years. And if we continue to just fund science and come up with better and better, possibly better and better therapies, treatments, that's going to be great, but it could be 10, 20 years before any patient see it. And we all know that's not what we want. We have family members right now and people on this call right now that need treatments. So we are acting with urgency. And because of that, we have decided to really focus on 2 programs. So the 2 programs that we are focused on are the drug therapy treatment out of Johns Hopkins that I'm going to talk about. And this slows the loss of sight for those with retinitis pigmentosa. And I'll explain that in a minute. And then our gene therapy treatment to stop the loss. This will actually stop. And some hope there is maybe some reversal of loss of sight for those with USH1C mutation of Usher syndrome. And again, I'll explain that a little bit more later. So to understand why we chose the first treatment, I want you to understand why, what it is, the difference between retinitis pigmentosa versus Usher syndrome versus USH1C. Some of the people on the call are really highly scientifically evolved, and this is kind of going to be simplistic, but bear with us because there are others that really don't know anything about this. So retinitis pigmentosa is a group of inherited retinal diseases, which includes Usher syndrome. It affects about 1.5 million people worldwide, which is about, relates to about 100,000 in the United States. The symptoms are in early childhood, adolescence, or young adulthood, different for different mutations. People begin to lose their vision. Most of the retinitis pigmentosa start with loss of night vision and decreased visual field. And retinitis pigmentosa, or RP, as it's known, can be non-syndromic, it can be syndromic, which is Usher syndrome, or it can be secondary to other systemic diseases. There are 50 plus known genetic mutations of retinitis pigmentosa. And like Usher syndrome, there's no treatments available for the vision loss. Sorry. Now, Usher syndrome itself is syndromic. So it affects not just the vision, which is the retinitis pigmentosa, the RP part of it, but it affects the hearing and affects the balance. It affects about 400,000 people worldwide, so a smaller population, and only about 25,000 in the United States. There are 14 known genetic mutations of Usher syndrome, and there are no treatments available for vision loss. Some would say technology offers, a treatment for hearing loss. And then if you go even more specific, USH1C, which is a mutation on the USH1C gene that affects about 3,000 to 5,000 people worldwide and about 300 in the United States. There are no treatments available for vision loss of USH1C. So you see it gets very specific. Now, the drug therapy treatment for retinitis pigmentosa, the reason that we were really excited about this is because it's not only going to help those with Usher syndrome, but it's going to help more people, as we saw as a bigger population. It's going to preserve the vision longer than if there was no treatment available at all, and I'll explain that. And we really think it might be one of the first approved and proven treatments to be available. And that goes back to our sense of urgency. There's a lot of great things that are out there, a lot of things being tested, but something that's going to help for almost everybody that has retinitis pigmentosa, they're just not that close. And if this goes along as planned, it'll be available in about 4 years. So our second treatment that we're going to focus on is the gene therapy treatment for USH1C patient group. Now, this one is specific to those with the USH1C mutation. It will stop the loss of vision, and with a deep hope, but not a known fact, that maybe it will bring back some vision. It's a chance. And then we think the way it is right now, what's out there right now, this potentially could be the first effective gene therapy for anyone with Usher syndrome. Even if it's going to be specific to USH1C, it'll be the first one out there. You may have heard about an USH1B trial that already was started years ago. Well, it is now on hold, but it's pretty much on hold permanently because they didn't have all the tools. And we hope we've learned from their mistakes. So I'm going to go back really and do a little more of a deep dive into the drug therapy for retinitis pigmentosa. So this was started at Wilmer Eye Institute at Johns Hopkins University by Dr. Peter Campochiaro. Now, Dr. Campochiaro is a well-respected researcher and clinician. He sees patients. He's a great person, and he's been working on anything he could figure out for his patients with RP for years. And so he started looking into NAC, which is called N-acetylcysteine, but referred to as NAC. He started looking into it, a decade ago. I know I read a paper by him when we first started doing research. I felt like it was so far off. It wasn't going to do a long-term stop of vision loss, so it wasn't one that we focused on. But because of where he is now, we are much more interested in it in the last few years. It is actually an over-the-counter supplement. You can buy it off the shelf. And it also is used in large quantities as an acetaminophen overdose. So if you take too much Tylenol, they give you a really high dose for a short period of time in the hospital. But because of all this, there's already long-term safety information at some dose levels available. So this makes it really attractive because it makes it easier to get through the FDA. So really briefly, just to understand how NAC works, I'm going to do a quick lesson for those, just a refresher for everybody who knows, and then for people who might not be aware or remember how the disease progression for Usher syndrome, specifically for retinitis pigmentosa, works. Is basically the retina is made up of photoreceptors. So you have what are called rod photoreceptors and cone photoreceptors. So the rods provide your vision in low light and in the periphery. Your cones are your central vision, and they bring color and clarity, okay? So most RP mutations affect the rods first. Not all, but most of them. And Usher syndrome is one of those RPs that affects the rods first. What happens is the rods die off, and what they do in the eye is they're not eating up oxygen anymore. So they cause oxidative stress in the eye, and that stress starts to affect the cones, and then the cones die off. So that's why you see with the rods dying off, you go from the picture on the left, moving down, you'll lose more and more peripheral vision until you're really kind of like a tunnel effect. But that tunnel effect is really the cones surviving. They're still alive and working. It's not optimal, but it's better than no vision at all. So that is why this type of a therapy is something that we want to pursue to get it out there to preserve some vision as long as possible. So Dr. Campochiaro's work, Dr. Campochiaro chose to stick with NAC because what he saw was that NAC reduces oxidative stress in the retina, and that way, if he can do that, he can preserve the cones for longer, and people maintain their central and color vision. So what he did is he started after his preclinical work. He did 2 trials. I have it as studies, but they actually are trials. His first was called Fight RP trial, and then he did a second extension study. And right now he's looking at a full phase 3 multi-center randomized double-masked parallel placebo-controlled study to evaluate the efficacy and safety of N-acetylcysteine in patients with RP. That's a lot of words, but it's all what the FDA wants to hear. Now, I want to add to the people who know about who have Usher syndrome or family members who know that there are no treatments out there. You are familiar with vitamin A. It's very controversial. Some doctors recommend it, others don't. Vitamin A was something that was studied 20 plus years ago by Elliot Burson. And the reason it's kind of controversial is because there was never a trial run, but there really wasn't a definitive study run. And this is why Peter Campancherio's clinical trial is so important, because he hopes to walk away from this in 4 years with a proven treatment that he can tell every doctor, and every doctor can tell every patient they have from the time they're young with retinitis pigmentosa, you can take this NAC, it will be safe, and it will help preserve your cones. And that's really important. So the way they're going to do this is they're going to be in approximately 30 sites around the world. And for those of you with Usher syndrome, if you want to know if a site's going to be near you, you can just contact me after this and I will be happy to let you know. They're going to use approximately 438 patients, and it's going to be over 4 years. And the beauty of this is it is going to be controlled, which means half of the people aren't going to get, or they're going to get a placebo. But the beauty of this is that they're writing the trial so that after 2 years, if they can show safety and efficacy, which I believe they will, they'll put everybody who's in the trial on the dosage of NAC. So that's really exciting. That means it would be available in 2 years to everybody in the study. So I love that. Right now, they just completed a giant grant application. I think it was 800 pages. They submitted to the National Institute of Health and National Eye Institute. It's for approximately $4.5 million per year. So you can see it's quite costly to run a clinical trial. I'm really hopeful for their grant application. We helped them a little bit, and I'm excited that we did. And you may have seen the study that we ran out there. Corey, my son, helped us put that together, and we ran it and got over, I think, 1,300 people to respond, people with RP. And we're really excited. Now, there's a possibility they don't get all the funding, or they need help starting. They don't have the funding yet. We're keeping all those options open, and we're saving up some money to help them out if they do. So let me just really quickly, for people who know, there's something else out there called NACA. It's from a company called Nacuity, and actually Scott sits on the board of Nacuity. I just want to explain the difference between NAC. NAC is N-acetylcysteine. NACA is N-acetylcysteine amide, I believe how you pronounce it. Both of these are based on the work of Peter. And Peter doesn't care which one works better. Peter just wants to get something into patients. So the reason that he's moving forward with NAC and not waiting for a company called Nacuity to complete their clinical trial is because NAC is already available. Like I said, the FDA likes that. They already have safety information. It can go quicker. NACO is not available over the counter at this time, so there was no existing safety studies, so they had to kind of start from square one. It's going to take a little bit longer. In fact, right now, they're not even testing it in the US yet. They just completed they've completed their preclinical work, and they just completed the phase 1 trial in Australia, I think at the end of 2019. And now they're working on a phase 1/2 trial. They expect to have those results by mid to late 2021. They will then have to go to a phase 3 and also be accepted by the FDA. So it may.
Hey, Susie, I just want to add one quick thing. That in Australia is strictly an Usher trial, just so you know, even though it's generic RP on Peter's stuff, we're doing it only in Usher patients in Australia.
Yeah, thanks for adding that, Scott, because what's important to that is it may take longer for it to get to all RP patients. If it works, for example, better and ends up in the United States, it may take longer to get to all RP patients, but it would still get to us, to Usher patients. So that's good for us either way. Okay, so now I want to go on to gene therapy. And we're going to, if you guys have any questions, please know we'll go back to anything you need to talk about. But I want to talk about this program because this has been pretty much since the beginning. We've been working towards this program. But right now, I want you to look at who we've got here in just general terms working on this for us. Odelia, who you know, I told you how it got started, but honestly, their goal of Odelia is to take any good proven science in from the lab into clinic. USH1C didn't necessarily have to be the one they choose to partner with, because if we didn't have enough information, we didn't have enough study, if we didn't have showing some efficacy or anything like that, there would be no reason for them to take USH1C on. But they looked at they independently looked at what we had and what we had put forward. And they said, this is a good program for Odelia to bring forward. So it's really exciting that we have Odelia involved. And especially not only because we have the expertise at Odelia, but they have an advisory board that includes the top gene therapy people in the world, plus drug development companies, pharmaceutical companies, top leaders in the industry across the board, you know, from everything from academia through for-profit. And they're all together on this board, and they are adding their expertise to our program now that we're under Odelia. So that's really exciting for us and very important. We also have Uwe Wolfram. Those in the industry or in Usher may have heard of Uwe before. He's been doing Usher research, specifically USH1C research, for decades. And that is all thanks to a group that's on the phone with us, Found Foundation, out of Germany, and the Sucrit family. So they've been funding him for decades. And the work that he's put together in the past and continues to do now is the key piece that's making this all move forward. Him and also his wife, Kirsten Nagel-Wolfram. He brought in Nick Kleimuk from Technische University in Munich. And he was able to clone the USH1C mutation and create our first large animal model, a pig. We also are working with a group called PigMod out of Czechia, the Czech Republic. And that's where our pigs are now housed and being very well taken care of by his group. And then addition to that, we have collaborators that include Jennifer Lentz and Rob Cohencoop, who are working on the natural history study, Tyson Lee, who's out of the National Eye Institute, who I think I mentioned him earlier, was doing work because of the Mendel family sponsoring him through Usher 2020. And his work, it's great because he's doing the organoid work, which means he's working with human cells, but because of things he's finding out, he's contributing to our gene therapy program for USH1C. And then other people like Maureen McCall and many others. Maureen is really a pig expert, which we need in our program. So that's very exciting. Now, I'm going to do kind of brief synopsis of gene therapy and explain it. So I'll go through this quickly. Again, some of you science people already know it, but if you'll bear with me while I explain it to others that might not be more as aware of it. You hear about gene therapy all the time in the news. Specifically, you hear about it even for treatments for blindness. You'll hear about it a lot. The COVID vaccine is the ones that's being used now is a type of gene therapy. So, you know, when you talk about gene therapy, you're talking about a lot of different things. But specifically what we're talking about is gene replacement therapy. We are replacing the mutation in the gene with a correct gene. So that's what we're going to be talking about for our programs. Right now, there are about 10 approved gene replacement or augmentation therapies in the US that are out there. That's not a lot, but I think I heard recently that they expect in the next couple of years up to 1,000 applications for gene replacement augmentation therapy, most of them in oncology. But the really exciting thing is the first ever FDA approved gene therapy was for a form of RP called LCA, which is a mutation on the RPE65 gene, not important, but just so you understand, it's a very specific mutation, just like the USH1C mutation. And the exciting thing about that one is it is working really well. And people are, children mostly, because that's what it affects, are not only keeping their sight, but they're actually seeing better. So really quickly, how does gene therapy work? Quick biology. Okay, so we all know DNA are the building blocks of life. But basically, DNA is a recipe book for creating proteins. So the ingredients in this recipe book are sugar, phosphate, and bases. And the reason I want you to understand bases is bases are when you see things and you see genetic lines of genetic code, there's just A, C, T, G written over and over again in different forms. It's adenine, cysteine, thymine, and guanine. Those are the bases that's part of what makes up the DNA code, okay? Now, genes are actually pieces of DNA. So genes are kind of like the recipes in the recipe book. Recipes are copied over and create what's called messenger RNA. You probably all remember this from science class. But what happens is when there's a copy, when the original gene actually has a mistake in it, meaning the line of code has a mistake, when it's copied over, the RNA that then goes on to create the protein, it's like a misspelling in a recipe book, and the mutation can't create the protein. So if you look at an USH1C mutations, so mutations on the USH1C gene, there are, I probably should have this number in my head. I think there are like 14 of them. Different mutations on the USH1C gene. They all cause USH1C or Usher syndrome. One of them is called 216G-A. So basically that's just on the 216 recipe code. If you want at the exon 216, the G was made into an A. And that little mistake in the recipe line is causing a problem with the protein. And the other one is that we hear about, most of the people on this call are either 216G-A or 238, 239. In fact, I think everyone has at least one of those mutations, or their family member does. That one is a duplicate C. So instead of just ending with a C, another C got stuck in there. So that's what the mutations look like. Now, if the mutations, whether the mutations occur or not, the RNA translates into a protein, and proteins are what keep our body going, keep everything going. What happens with a mutation is that the protein doesn't come out as this beautiful blue folded blob. It may only be a little piece of it. It may not exist at all, or it may create a protein that's different, and that protein then goes on to do something destructive. So what happens? So what happens with this is when you don't have a full protein in, when the USH1C gene does not create the correct protein, it actually creates because it's mutated, creates a smaller piece of protein. The protein that's needed to, let's say, feed the rods and feed the hair cells in the ear and feed the vestibular system does not exist. And that's why you have the loss of vision, loss of hearing, loss of balance. All right, now how does gene therapy work then? So gene therapy, basically, you just create a correct copy of how the gene is supposed to read. So instead of that A to G, you make it an A instead of the A to G, okay? Instead of a duplicate C, you take out that one C, and now you have a corrected gene. Now the way the gene therapy works is you take that corrected gene, okay, and you load it into something that's like a truck. It's a vector, which is basically a virus that's been cleaned out and empty. And now the virus does its job and goes to the cell, and it delivers and dumps into the cell its payload. And in this case, its payload is a corrected gene. And that corrected gene then goes in and it corrects the DNA, and now the DNA replicates, transcribes, transcription, whatever. It goes on to create the correct protein. All right, so to understand gene therapy and why we want to do it for USH1C, we want to look at the successes out there. And the one almost everybody has heard of is Luxturna. It's for something called Leber's congenital amaurosis, or LCA. So in the news, you constantly hear about children, blind children are seeing now, and things like that. It's been around for, I think they really started reporting on it in the mainstream news about 3 or 4 years ago. I saw something in National Geographic. And the reason it's so exciting is because it is keeping children from losing their vision, and in many cases actually gave them back some of the vision they lost. So why did they choose to go for this one mutation? So we talked about RP has 50 known mutations, and so why did they choose the LCA, or specifically the gene mutation that they chose, the RPE65, which is the actual mutation? They chose it because it was a really small gene. So that means it fit in vectors very easily. They chose it because they already knew that the vector it would fit in would deliver really well to where it was supposed to deliver. They chose it because it only had one isoform, which is basically the protein that's developed actually comes in different forms. It's very complex and I don't really understand it, but sometimes genes create multiple isoforms, and that makes it really difficult to know what isoform to use. This one only had one, so it's pretty easy. They chose it because it was a fast progressing disease. Kids get it, kids are born with it. They start losing their vision very early in life, and by the time they're 10 or 12 years old, they're blind. So being fast meant that they could tell if something was working. And they chose it because there was a natural occurring mutation in a dog model, which is really incredible for them and not what we had. They put a natural history study together, which was important. And the most important thing that happened to them is this was one of the first gene therapies. So this was called proof of concept. People wanted to do it because, hey, if we can prove this in this small group of children, we can then take it and make a lot of money off of it, doing it some other way for something else. This is how the biotechs and pharmaceutical companies look at it. So the challenges for LCA Luxturna was that it took well over 10 years to develop. And that doesn't include the decades of research that went on before that. It cost $20 to $30 million. That's a lot of money, which is very typical of any type of clinical trial. And now the patient costs for this treatment is, I think it might be a little less now, but it's about $850,000, which is tremendous. So when we look at that and we say, okay, why do we want to do gene therapy for USH1C? Because we have challenges too. It's a very complex disease mechanism compared to LCA, which affects which vectors we choose, which promoters we choose, that sort of thing. It also has multiple isoforms, so we have to figure that out. Usher syndrome, as we all know, is a slow disease progression. It's much harder to prove efficacy of something when it takes longer for something to happen. There was no naturally occurring large animal model, and the proof of concept is no longer needed. So we're not going to have that advantage that Luxturna had of saying, hey, proof of concept, big pharma, big biotech, come in and help us pay for this. And there is an even smaller patient group in the USH1C gene than there was in the RPE65. So how are we going to overcome all of these things for our gene therapy? And how have we? Well, how have we done it? We've already reviewed studies on the disease mechanism, and we've developed a plan to test multiple vectors and promoters for both safety and efficacy. We have completed studies on the isoform expression, when I talked about earlier. And although there's not 100% guarantee of anything, we came to a collaborative decisions based on the input from a lot of really smart scientists on which isoform to use in our gene therapy. You'll see a picture right here. We created a successful large animal model with a phenotype, which means this animal shows that there is retinal degeneration and it has hearing loss and it has balance issues. So it has a really strong phenotype for Usher syndrome. And I show a picture of our beautiful pig model here. She's a wonderful mother who has given birth to many piglets, and they are all very well taken care of at our facility in Pigmod. I have to tell a story really quickly about the woman who takes care of all of the pigs when they are pregnant, because they do have balance issues and they are deaf and they are losing their vision. She cares for them like they're her own children and makes sure that these pigs have a safe and healthy birth, and then they take care of their little piglets. And I'm very thankful for that. So, and then also we are overcoming this because we have currently developing a natural history study through Jennifer Lentz in Louisiana for the USH1C patient population. She's also working with Rob Cohencoop out of McGill University in Montreal. And the best thing, as I told you earlier, we've partnered with Odelia Therapeutics to bring this gene therapy treatment from its concept. And our hope is into clinical trials in just a couple of years. We are working on a very accelerated time frame. So what's left to do? So right now we are trying to find out after Peter hears back from NEI for his grant application, we'll know what funding is going to be necessary for the NAT clinical trial. That's going to go on from 2021 through 2025. And even if we don't fund it, even if they don't require funding, we will be available then for support. We are currently funding the gene therapy preclinical work that's being done with the group that I showed you, work being done in Germany, in Czechia, but also in collaboration with the work over here in Odelia. And a lot of this, the funding that, a lot of the funding coming right now for the Germany side of the work is coming out of the Found Foundation, and we thank them for that. But some of you have also participated in funding that's going to go to keep the pigs going because we'll need them for testing in Czechia, as well as the vector development, which is a really huge and expensive piece that's going to go on here in the United States. So we will continue funding all that. And we hope to get to the end game by 2023, 2024 at the latest, and find someone to help us put this into a clinical trial, because that's going to be the big money, which we are not going to be able to fund. As we talked about before, maybe $20 million for a clinical trial. But if we can go in with some of that funding available, we'll be more likely to find a partner in a pharmaceutical and biotech. So we're preparing ourselves to have some funding available for that. And we are continuing to explore alternate treatments. We're not giving up on other things. We just really want to focus so that we get something to patients sooner. As far as everyone on this call, our partners, our families, our donors, we appreciate your continued support as much as you can do. We also appreciate any type of awareness you can raise for Usher syndrome. It helps bring more people in to support us. If you follow us on social media, you like, repost, comment, whatever you do to help build our social media base. We're actually starting a Give It Up for Sight program that we need champions for that. So I would love it if we walk away from this call and people let me know off the call that you're willing to be a Give It Up for Sight champion. I'll explain what that means. It's all about driving people to social media and driving those people to make small scale donations. Kind of the same way that the Ice Bucket Challenge worked. So, but I have the tools available, and if you become a champion, you'll receive all those tools. Oh, I have some pictures. Can you guys see me? I think you can. Here, but I'll show you afterwards. And you get a nice Give It Up for Sight t-shirt if you become a champion. And then finally, if anyone is actually a patient on the call and would like, Odelia is running a hashtag Cure Rare campaign starting in February, because that's Rare Disease Month. And they're looking for people that are willing to just have their picture put on their social media that says hashtag Cure Rare and says, what is it that you would, why do you want a treatment? For example, I want to still be able to see the stars at night. So that's the kind of thing. So that's it for the presentation. I want to thank everybody for being on there. We have time. We can have some questions if anyone has anything. I really want to thank all of you for being a part of this. Let me just stop sharing this screen. And just if you want to ask a question, just unmute yourself and feel free to do so, or any comments.
Hey, Susie, it's Andrew. Thanks
Hey,
so much for the presentation. Is Usher 2020 still supporting going forward ASO research?
Yeah, so that's such a great question. So right now, Jen is still trying to get her ASO through. And so she's really focusing on getting an NIH grant directly, and we will support her in any way that we can to get that, and we still do. So what she did is ASO is specifically the 216G to A mutation, and she expanded her research because that was such a small patient population to include the 238, 239 mutation as well. I don't think she had the results that she wanted. So I think what she's going to focus on is just the 216G to A, trying to get a clinical trial for that. We are not giving her funding to that at this time because it's so specific and because there's not a path unless she can get somebody else to help out, like the National Eye Institute. So,
and actually, I'll just add something, Susie. So at the inflection point when we decided not to give her any more money for this was we pushed her to skip this exon 3, which included 238 and some other mutations. So it would include our entire group. And she did and got a funding for that. And the testing hasn't proven out yet. If it does, then we'll switch back to focusing on making sure that is, because it won't help most of the people on this call. So we're only doing things that help the USH1C and our community in whole.
okay, so hopefully that answers your question. I think, let's see in the chat. They're saying, I have a quick, okay, Katie, quick question on the vitamin A efficiency and safety trial. Has a synthetic control arm been considered in lieu of the double-blind control placebo? Okay, so Katie, you asked about vitamin A efficacy, and
sorry, it's super loud here. So basically, you mentioned the clinical trial for the vitamin A efficacy and safety, right? The one that
yes. So I didn't want. I'm sorry, I may have confused you a little bit. What I talked about vitamin A was what we're doing and what Peter's doing with the NAC trial is for safety efficacy. Vitamin A has never had that trial and nobody's running it. So that's why we're saying the NAC trial is so important to be done correctly, which is exactly what Peter's doing, so that there's not all of this misinformation and confusion out there like there is with vitamin A.
Oh, I see. So it's not a vitamin. Sorry, it's not the vitamin A efficacy trial. It's the NAC trial. What's NAC again?
So NAC is N-acetylcysteine, and I want to tell everybody who's a patient out there, it's on the shelf. Do not go get it. Okay.
Oh, got it.
So what this trial will do, will prove safety and efficacy. It's in a certain dosage. It's in a controlled environment that it's produced. So if you go get NAC off the shelf, you're not sure what you're getting. And what Peter's doing is making sure that this is created with all the standards that are needed for a drug. And vitamin A, NAC on the shelf is a vitamin, basically. It's a supplement. So it's not going to have that in it. So if everybody can hold off on taking NAC, hold off. In 4 years, we should know. Now, hopefully, if you're out there and you're in and you qualify for it, maybe you can get in this trial. And like I said, I'm happy to tell you where to go as soon as it's ready. Does that make more sense?
Yeah, totally. The question still holds though for the NAC trial then, because you mentioned it's a double-blind placebo control, and it sounds like for that trial particularly, they're like the inclusion exclusion criteria are probably pretty broad. Would a synthetic control arm qualify for such a trial? In which case, you don't have to wait 4 years for those that are in the control to actually take the medicine.
Well, actually, it's not broad at all. So it's non-genotyped. Meaning anybody, it doesn't matter what genotype, and the only exclusion criteria is age parameters and visual field parameters.
Yeah, and I would say age parameters, I would say visual field parameters. So everybody who's got young kids out there, you're going to have NAC to use in a few years. You can wait. Your kids don't need it now. It's for central vision. You're going to be okay. You're going to have, that's why we're so keen on supporting this, is because we know all of you out there with young kids, you're going to have this, and it's going to help preserve their central vision. And that doesn't seem as important right now, but it is important. So, and it will be important. So it's going to be out there quicker. And so that's why we really want to see this thing go through. Okay, let me just make sure there weren't any more questions. Anybody else? I see some kids, I hope everybody can see on the screen, some of the kiddos that we have that are why we're doing all of this work. It's great to see everybody. Ah, there's a kiddo. Here's another kiddo. So that's why it's so important. And,
Hey, I'd like to just say thanks, Susie. She spent a lot of time putting this presentation together for everybody. This wasn't like a off-the-cuff thing. She's been locked down for a week, putting all this data together in a centralized form to be able to share with you guys.
I hope it was clear. I hope it, I know some of you are very scientific and know this stuff, but we had a lot of different people on the phone. So I hope it was clear, and I hope our purpose and our path is very clear. That's what we're trying to do, is have a path and get there. Urgency. I see family members waving to each other. Great. All right, if there's no more questions, thank you guys so much. We really appreciate it. I hope I get some emails if anyone wants to be a champion, or if some of the patients want to be involved in the rare Cure Rare program, social media that Odelia is putting out there. Please let me know. I'll hook you up with the right people to talk to, and I'll help you through being a champion for Give It Up for Sight. It's a way to continue to raise money and to bring in new people to the program. And we'll stay in touch. But if you ever have a question, please feel free to contact me. Happy to. And
we'll send a link for this recording, and we'll also add the transcription to it, and make sure that there's the closed captioning, and if not closed captioning, the full transcript.
Yeah. So guys, I do apologize for that. We tried. It's the first time we've done it. So please bear with us. Next time, hopefully, we'll be better. All right. Thanks, everybody. Take care.
Thanks, Susie.
Thanks. Yeah.
Bye.
Bye.